Welcome to this new video where we quickly learn how IEC 61499 is changing the industrial automation paradigm. This video is a quick introduction aiming to understand what IEC 61499 is and why it is the correct step towards Industry 4.0. This is not a technical deep dive into the details of the standard. To set the stage, let's start with the Purdue Model, a reference model that illustrates the architecture of industrial automation systems. This model breaks down industrial operations into multiple layers, from level 0, which includes sensors and actuators, to level 4, which encompasses enterprise systems like ERP. Automation layers have evolved to ensure real-time data flow and robust control. Within this model, controllers play a critical role. And to better understand this topic, let's imagine 4 internal layers inside a controller: an OS/firmware layer, where the core software manages hardware resources; a communication interface layer that helps connect the controller to other network components; an application runtime, a layer that hosts, runs, and interprets the logic programming language. Finally, on the top is a control application layer, where we have user-defined logic applications designed to execute industrial tasks. This understanding is crucial for evaluating how IEC 61131 and IEC 61499 manage control systems differently. Now that we've introduced the Purdue model and controllers layers, let's focus on the top 2 layers of control applications, specifically the runtime and control application. These layers are managed by 2 standards, IEC 61131 and IEC 61499. IEC 61131, established in 1993, has been the cornerstone of industrial automation for decades. It standardized programming languages for programmable logic controllers, PLCs, making it easier for engineers to develop and deploy control systems. However, IEC 61131 also led to the development of more proprietary control logic. This happened because while the standard defined the programming languages, it left much of the implementation to individual vendors. As a result, each manufacturer created their own unique execution environments and proprietary extensions, leading to vendor lock-in. This proprietary nature has made it challenging for users to switch hardware without costly rewrites or re-engineering efforts. On the other hand, IEC 61499, introduced in 2005, provides a more modern approach focused on distributed control systems. Unlike IEC 61131, IEC 61499 is designed with openness and portability in mind. It uses function blocks to achieve modularity, enabling control logic to be moved and reused across different platforms with minimal changes. This decoupling of software and hardware ensures that control applications are no longer tied to a specific vendor's hardware, promoting flexibility and vendor independence. This brings us to comparing IEC 61131 and IEC 61499. These 2 standards represent different eras of control system technology. Let's dive into some essential differences. From an architectural point of view, IEC 61131 follows a controller-centric architecture where control logic is tied closely to the hardware. On the other hand, IEC 61499 supports a distributed control architecture, allowing control functions to be spread across different devices and locations. This user-friendly approach empowers users to have more control over their systems. On the execution model, the IEC 61131 uses a cyclic scan model where the control logic continuously scans inputs, executes the logic, and updates outputs. The IEC 61499 adopts an event-driven execution model. Function blocks execute when triggered by specific events, resulting in more efficient use of resources and faster response times. This will lead us to the reusability difference, where IEC 61131 is limited due to the hardware-specific nature of the applications. IEC 61499 object-oriented function blocks make reusability simple and scalable. Using the same blocks in different projects or systems saves significant engineering effort. To understand whether IEC 61499 is required or not, we need to look at the current challenges and needs better. Starting with the industry's current challenges since introducing IEC 61131. First, we are pressured to reduce costs. Cost reduction has been an ongoing challenge for industries. The traditional control systems designed under IEC 61131 are often rigid, making changes and updates costly. Maintenance costs, upgrading hardware, and the need for specialized engineers to manage complex PLC systems add to the financial burden. To worsen the situation, we have increased product variants and shorter product life cycles. In today's competitive market, manufacturers are expected to manage a broader range of product variants with much shorter product life cycles. This means frequent reconfiguration and adaptation of production systems, which is challenging with rigid IEC 61131 based systems. This also sometimes means more complex spare parts management. Fluctuating demand, energy, and raw material prices are all factors. Uncertainty in market demand and fluctuations in raw material and energy prices require manufacturing systems to be agile and scalable. However, systems designed on IEC 61131 lack this flexibility, as they are tied to a specific hardware and logic framework that limits rapid scaling up or down. We can't forget the fact that the automation industry is increasingly under pressure to comply with stringent safety, environmental, cybersecurity, and operational regulations. Compliance often means making frequent updates to control systems, which is cumbersome with the tightly coupled nature of IEC 61131 solutions. Then comes the change in the nature of the workforce in industrial automation. There's a need to attract new talent, but younger generations often hesitate to work with legacy systems like those based on IEC 61131, which require specialized and less familiar knowledge. Finally, as mentioned before, IEC 61131 tends to tie end users to specific vendors due to proprietary hardware and software dependencies. This lock-in increases switching costs and limits the flexibility to select the best technology for a given application. On the other side, new technologies are required to be integrated into the industrial systems. Customers increasingly demand machine learning and data science to make their operations smarter, predict maintenance needs, optimize production, and enhance efficiency. Traditional automation architectures are often closed and rigid, making it challenging to integrate advanced data analytics. Augmented and virtual reality improve operator training, maintenance, and troubleshooting in automation environments. These tools rely on having access to real-time system data. Digital twins help simulate performance, predict issues, and optimize processes. To be effective, digital twins also need real-time data and must be able to mirror the operational behavior of the physical system. Edge computing is essential for processing data closer to the source, enabling quicker response times, reducing latency, and alleviating the burden on centralized systems. Traditional systems have not been flexible enough to accommodate any of these technologies. Now, let's explore how IEC 61499 can support us in facing these challenges and new needs. Let's take our time to dive into one of the core features of IEC 61499, Its event-based execution model, which plays a crucial role in achieving plug-and-produce capabilities and making automation more adaptable and efficient. Event-based execution fundamentally differs from the traditional cyclic scan model in IEC 61131. In the IEC 61131 model, the system continuously scans inputs, processes the logic, and updates outputs, regardless of whether or not any significant change has occurred. This type of continuous updating is resource intensive. It demands constant computing power, which makes it challenging to efficiently implement AI models or advanced analytics, as these also require significant processing capabilities. In IEC 61499, the control logic is event-driven. This means that function blocks are triggered by specific events, such as a sensor detecting a change, the start of equipment, or even an operator action, rather than being continuously scanned. This event-driven approach aligns much more closely with the IT world, where most computer systems and software applications operate event-based. Think about your Excel sheet. It doesn't continuously refresh every piece of data. It reacts when an associated cell is updated, or even with a refresh request. This is similar to how an IEC 61499 control system reacts when an event occurs. So, why does this matter for industrial automation? Let's look at some key advantages. Efficient resource usage. The system can allocate computational resources precisely where and when they are needed, because tasks are executed only when triggered by relevant events. This reduces the continuous demand for processing power, unlike IEC 61131's scan-based execution. In a traditional system, running an AI model would mean it needs to be constantly evaluated during every cycle, even if there is no meaningful data change, resulting in a substantial waste of computing resources and sometimes not enough resources. By reacting only when required, IEC 61499 allows AI models, augmented realities, and digital twins to be integrated and executed more intelligently, reducing the computational load and improving system responsiveness. As a consequence, reduced hardware requirements become another advantage. You can even use embedded controllers in smaller devices like wireless sensors or transmitters that might not have the capacity for heavy-duty computing, but can handle event-driven tasks perfectly well. This makes distributing controllers across the entire network possible, with control logic running directly on sensors, transmitters, controllers, and even in the cloud. This results in a more scalable and distributed control system instead of centralizing all control tasks. Different parts of the control logic can run where it makes the most sense, at the edge, directly on a field device, or in the cloud. This allows control functions to be executed closer to the data source, reducing latency and making real-time control more effective. Ultimately, this feature will support adding or removing devices to become much more accessible. For example, when a new sensor is installed, it can generate specific events that the control system can recognize and respond to immediately. This concept, often called plug and produce, allows systems to adapt dynamically without requiring a complete reprogramming of the control application. It's about giving industrial systems the same flexibility we see in IT systems: modular, adaptable, and responsive to changes. In summary, event-based execution provides a modern, efficient, and scalable way to manage industrial control systems. It allows controllers to be distributed across various devices, whether it's a small sensor, a transmitter, or a powerful edge device, using computational resources intelligently and economically. By triggering control actions only when necessary, IEC 61499 not only makes AI integration feasible, but also makes distributed control more accessible by leveraging less powerful, cost-effective hardware. In IEC 61499, the software is decoupled from hardware. This means the same control logic can run on different hardware platforms without modification, drastically reducing switching costs and eliminating vendor lock-in. This portability ensures that upgrading or switching hardware does not require complete rewrites, which saves time and resources. Also, modularity and reusability blocks simplify regulatory updates. For instance, if a new safety regulation requires additional checks, it can be integrated as a separate device or function block without overhauling the entire system. The decentralized control approach also ensures compliance on different production levels, making it easier to adapt specific parts of the system to meet regulatory requirements while minimizing downtime. In conclusion, IEC 61499 breaks away from the proprietary lock-in often found with IEC 61131 by providing a vendor-agnostic open architecture that allows customers to choose the best hardware and software solutions. It is a major step towards open systems. The object-oriented nature of IEC 61499 makes it easy to develop reusable software components, known as function blocks. These function blocks can be used across different projects and adapted for various purposes, reducing engineering time and cost and ensuring application consistency. Also, modern programming paradigms such as object-oriented design and software reusability make IEC 61499 more attractive to software developers more familiar with modern IT methodologies. The application-centric approach reduces the learning curve, allowing new engineers to work at an abstract application level rather than dealing with specific PLC hardware. This makes attracting new talent and adapting to the evolving workforce easier. The control communities should play a role in promoting the system's openness. One of these known organizations is UAO. UniversalAutomation.org is an initiative that encourages the adoption of open, interoperable automation standards. It supports IEC 61499 in creating a genuinely open automation ecosystem. The organization focuses on the third layer, application runtime. It aims to provide a standard runtime environment that allows applications to run across different platforms, encouraging using best-in-class technology from multiple vendors without vendor lock-in. By establishing a reference implementation of the IEC 61499 standard, UniversalAutomation.org is pushing for a unified, open system where control applications are portable and compatible across various hardware environments. The organization combines the efforts of vendors, end users, and academics, and their runtime also goes one level deeper by providing data through a common open communication protocol, OPCUA. Let's address some of the common concerns regarding IEC 61499 and how these are being tackled. High cost and complexity of industry 4.0. IEC 61499 simplifies complex integration through plug and produce capabilities, making it easier to adopt Industry 4.0 strategies. Hardware reaches end of life. The hardware-software decoupling makes it easy to migrate applications to new hardware, ensuring longevity. Repetitive effort. The asset-centric reusable function block approach allows engineers to reuse software components, reducing the need to recreate simple process control functions for every project. Managing multiple vendors. The open and standardized runtime environment of IEC 61499 allows using a unified library across vendors, minimizing costs associated with managing multiple suppliers. In conclusion, the journey from IEC 61131 to IEC 61499 represents the evolution of automation from rigid hardware-bound solutions to flexible, open, and distributed architectures. IEC 61499 addresses the critical challenges of today's automation landscape, ranging from the need for open systems and reusability to portability and scalability. The shift towards a more open ecosystem, as championed by initiatives like universalautomation.org, aims to give companies the freedom to choose the best tools, reduce costs, and future-proof their automation investments. The industry stands at a turning point, moving towards greater openness, interoperability, and digital transformation. IEC 6-1499, with its innovative architecture, is ready to lead this transformation. Thank you for your attention. Please feel free to contact me for any questions.